My intention is to create a video or a series of videos that describe the basics of graphics programming, specifically using WebGPU, Rust, and WGSL. I wanted to learn more, and I thought I would try to combine some of the more disparate pieces of knowledge and reiterate some of what I was struggling to grasp from other sources. Ideally, this provides an entry point into shader and graphics programming, which is perhaps undermined by the fact we'll eventually be working with the previously mentioned languages and frameworks, but here we are. I hope people find this useful or at least interesting. I often hear the term shader used to describe any graphical effect in video games, and that honestly probably isn't as far off as I had first assumed. Shaders are often used to add lighting and special effects to base 3D models, but more generically, a shader is just a program that runs on a graphics card. Traditionally, we use the graphics card to, well, draw graphics, so we'll be looking at rendering pipelines of the GPU before the more general compute pipelines. Before we get to any of that though, we'll need to understand some basic concepts about how we represent, store, and manipulate graphics data. Elements are drawn to the screen by describing points in space called vertices. A single vertex in mathematics is an intersection between two or more lines, rays, segments, edges, etc. For our purposes, a vertex will mostly be defined as the corner of a triangle, since that's how GPUs are designed to build geometry. Our vertices build triangles, and the triangles build meshes that describe the shape of 3D models. Each vertex has an associated position in 3D space, but can also hold data like texture coordinates, color information, lighting information, and anything else that we may decide is useful. This data describes the shape of our model using position coordinates and allows us to paint the pixels around each vertex using the remaining information. The order that we define the vertices describes the front face of the triangle in the form of a normal vector, which is useful for calculations like lighting, collisions, and performance optimizations. It points perpendicularly to the triangle's face and towards the outward direction of the surface, though outward may make more sense in the context of a full model. Whether a clockwise or counterclockwise vertex orientation points up, outward, forward, etc. is decided in our program and called the triangle's winding. Counterclockwise tends to be the standard, which matches the right-hand rule convention commonly used in vector mathematics. When holding out your right hand, your fingers curl with the winding direction, causing your thumb to point in the direction of the normal vector. In larger triangle meshes, vertices are often used multiple times to describe different triangles, so we can easily save resources by indexing our vertices and referring to them by their index number rather than redefining their full list of attributes each time we need to call them. The way a triangle or triangles are constructed from these indices and attributes is called a topology, and the most basic form is called a triangle list, which groups each set of 3 vertices together as a unique triangle. Adjacent triangles often share vertices, so more efficient topologies such as triangle fans and triangle strips can be used to greatly reduce their memory footprint depending on the size and shape of a mesh. There are also topologies that allow us to define our primitives as points or lines rather than triangles, but the implementation depends on the target device's hardware, so they aren't used as often due to the resulting compatibility issues. A vertex can contain color information, or pixels can be colored programmatically, but when working with 3D models, it's more common to assign a texture to an object. Textures are images that are stretched across a surface by assigning UV coordinates to each vertex and interpolating the pixel values between them. We'll talk slightly more about interpolating pixels and triangles in the render pipeline section. UV coordinates map from 0, 0 at the top left to 1, 1 at the bottom right. As an aside, as far as I understand, UV doesn't seem to mean anything. The letters U and V are just commonly used variable symbols in vector-based mathematics like linear algebra. A 3D model is the combination of all of these concepts that ideally completely describes the object that we're trying to draw to the screen. The 3D models I use are stored as object files, and the importing process gives us the stored vertex positions, UV coordinates, normal vectors, and the indices for each triangle. I'm using the tiny object loader crate TOBJ to handle all of the importing, but if you're interested in glancing at the object file data, it's mostly made up of numbers describing the previously mentioned attributes. This one, generated with Blender, starts with a few comments, followed by the vertex positions marked with a V, the normals marked with VN, the UV texture coordinates marked with VT, and the faces marked with an F. It also has some information about what material the object is. It represents light interactions like reflectivity, but I don't use it for this project. I found out during this project that artistic 3D models in programs like Blender are often built as quads instead of triangles. So when you export them, they either need to be converted to triangles by the exporting program or by a process in our program. You can actually see this in the previously mentioned object file. Each face is defined by several vertices that are in turn defined by a position index, a texture coordinate index, and a normal index. These indices point to the vertex values listed in the tables above the face declarations. In the example, there are 4 of these vertices rather than 3, since I didn't select the triangulated mesh option when exporting. This ended up costing me an hour or two trying to figure out why my model was loading in as a ball of brutally stretched, spiky triangles. You may also need to redefine the axes directions when exporting your model depending on your target coordinate system. In order to be drawn, a vertex must be within the boundaries of normalized device coordinates. This just means that any vertex you want to be drawn on the screen must end with a position within the ranges -1 to 1 for x, -1 to 1 for y, and 0 to 1 for z. The bottom left corner of the screen corresponds to -1, -1, z. The z value represents the depth value of the object, and the near plane is 0, 0 by default, but can be set to 1 with the render pipeline options. Remember that these values and settings are all for WebGPU and may be slightly different for other graphical standards. In a full graphics program, there are usually several steps before a vertex reaches this stage. Models start in a local coordinate system and are shifted with matrix transforms into a world coordinate system that allows us to place them in the scene. This is to say, when you create a model, it's probably designed with its vertices centered on the origin 0, 0, or built from that center point somehow with its own scale and spatial orientation. This is its local coordinate system, often called object or model space. In the world, however, it will be placed in an arbitrary spot, possibly even needing to be carried or moved freely from one place to another. We may also need to grow, shrink, and rotate the object as necessary. This is the first stage of transformations, and it results in all of the objects being placed in a global coordinate system called world space. The world then needs to be transformed so that the desired section is within the view of the camera in order to represent the camera moving through space and pointing in the desired direction. This requires another set of transformations that result in another new coordinate system called view or camera space. Lastly, a view matrix maps the user's view of the world from the camera into the bounds of what will be drawn and projected onto the screen. The result is called clip space and maps the view of the camera into a cube shape. Clip space has a built-in scale factor that then scales the resulting cube view into the normalized device coordinates. Anything outside the boundaries is clipped from the scene and not converted to pixels later on. There is also a coordinate system called screen space that represents what pixels the objects map to on the user's device, but it happens after the stages we're currently interested in. Forgive me if the exact terminology isn't fully correct, but this hopefully gives you an idea of the process of how a model's vertices get prepared for rendering. The view matrix in the previous section is often described as a camera, since it acts as our eye into the world containing our models. For most applications, the camera will attempt to mimic how a lens, like our eyes, views the world. This is called a perspective projection, and it replicates how an object's perceived size changes with its distance, giving us a sense of depth within the world. You can picture this projection by imagining a single point in space in front of our screen that projects a ray from the point and through each pixel of the screen until it hits an object or reaches the view distance limit. At this point, the pixel is colored by either the point on the object the ray hit or a background texture. CAD programs often also include a view that focuses more on allowing us to see the true shape and measure of an object's features rather than its relative depth in 3D space. This is called an orthographic projection and can be pictured by imagining that every pixel on the screen casts a ray straight back from the screen and completely orthogonal to the screen. Each pixel is again colored by the object hit by its corresponding ray or the background if no object is hit. Both projections map a slice of the world onto a flat surface called the picture plane, the screen, while clipping objects that are too far to render. A perspective matrix maps a pyramid frustum shape to the screen, while an orthographic projection maps a rectangular prism. I think that's as much as we'll do for this video. The next one should be about the render pipeline and how it manipulates data through the several stages of the graphics card. I plan to make an accompanying text version of these videos, since I personally find that an easier resource to learn from when actually implementing new concepts. I hope this was helpful, and I hope to see you in the next one.